All right, guys, I'm going to go ahead and get started. Everybody, welcome. It's good to see you all again. Sort of see you, or at least have you on the computer for some of you. Thanks, Curtis. It's got the wave. I appreciate that. All right, so first off, just thank you for letting me kind of alter the schedule a little bit today. I had a important family thing that came up that wasn't on my radar, but that was important for me to be a part of. And so thank you so much for letting me slightly adjust. I hope it didn't throw off anybody too bad. For those of you that aren't attending right now, again, I'm going to get this recording up as quick as possible, hopefully by our normal class time, so that anybody not here can watch it. Also, any of you that are here, if you hear any talk about anyone that didn't get my message or anything like that, just please kind of spread the word that I will have this posted on Canvas right away. So people can view it. But anyway, I really appreciate you adjusting. It's not something I normally do, but I appreciate your willingness and appreciate you being here. First thing I'll go with is the test. Everybody got their test done, so good job on everybody getting it done. It went good. We had, kind of a normal bell curve. There were some of you that got 100% on it, and then we had some that maybe were down close to maybe like a C plus, B minus. So overall, you guys did really well. I'm proud of you guys for how well you did. There were a few of you that texted me early on when you took the test to inform me of some things that were wrong with the test. And so I fixed those things. And those of you that contacted me or anybody that got wrong answers because of that, I gave full credit and made adjustments. So thank you. Always please correct me when you see something wrong. I'm surprised that after 5 years of doing this, I still run into things that are wrong that nobody catches. So that's just, I'm human. It'll happen. So thank you for doing that. I also would encourage you to remember to take your test, do your test corrections. Again, that's part of the learning process, to go in and look at what you missed and have to study it. It gets into your brain better. So please do your test corrections. And then also, of course, all of the math stuff remains open and will remain open throughout. So we're going to go ahead and get started quickly. The other thing I will say for today is that I do not want you to be late for Shauna's class. Please don't do that. She'll have my hide. So when 2:30 hits and you need to be over there, just please leave. I'll try to remind everybody, but just get off. If I'm still talking, which is probably likely, I will just finish out the lecture and then you've got it on recording. I don't want to go into her time. But I'm excited about this lecture because we actually get to talk about the gamma camera, which is the thing you use 90% of the time. We get to get into the physics and the instrumentation and how this thing works and help you understand the tool that you're using every single day when you go to clinicals. So I'm really excited about that. So let me get my slideshow going. I will share and then we'll just dive into it. All right, can you guys see my slides? Somebody give me a thumbs up. Okay, see head nods. Good. All right, excellent. Awesome. Let me make a couple other adjustments to my screens that I need and we will dive in. All right, so like I mentioned, we're going to talk about gamma camera today. What we're going to do first is there's some principles. So our next lecture, this lecture we talk about gamma camera, and then our next lecture we're going to talk about a bunch of other tools that you use, like your survey meters and other things. Anything we use in nuclear medicine, the name of the game is radiation detection. Whether that's a camera or whether that's any other instrument we use, we're trying to detect radiation. So I'm going to spend the first few slides talking about some general principles about radiation detection equipment. It might seem a little bit convoluted. Don't worry about it. I'll go through and kind of explain some general principles. And then as we go in talking about the gamma camera, I'll reference back to those and it will make a lot more sense to you when we do it that way, okay? So radiation is used in nuclear medicine, or radiation detection is used in nuclear medicine to perform a variety of tasks. We do diagnostic imaging, we do therapeutic dose delivery, and we also have equipment calibration. Those are kind of the several things that we do. I have a list right here. I like this list because it kind of shows all the many things that we use, the equipment that we use in nuclear medicine. You'll notice it starts with like your dose calibrator, your survey meters, your ionization chamber, surgical probe, thyroid probe. We're going to cover a lot of that in the next lecture. This one, we're going to focus solidly on the gamma camera. You'll notice here, next lecture, we'll talk a lot about gas field detectors and the principles of how they work. Today, we're going to talk about scintillation, which is how a gamma camera works, okay? That's also going to apply to a thyroid probe and a well counter, which we'll talk about next time. So I'll reference some principles, but you're going to learn the main principles of scintillation today, and that's how a gamma camera works. And then, of course, in later lectures, we'll get into PET. And we won't talk about dosimeters really until summer. That's in our quality assurance course. You're welcome to learn about those. They're not really too detailed, but we will cover those then and not now. All right. So I kind of mentioned before, the purpose of nuclear instruments is to detect and record gamma events. We do that in space. In other words, where did it happen? We do that in time. When did it happen? Energy, what was seen? Can we identify the difference between TEC and I-131 or different nuclides that we use? And then concentration, how much of that thing is there? So that's what we're trying to do with our detection. So the kind of properties or principles, the first one is detector efficiency. We also call it sensitivity. To be honest with you, I refer to it more as sensitivity, especially when we're talking about a gamma camera, but it's the efficiency of how well it works. We're going to talk about geometric efficiency, intrinsic efficiency, and then photo peak efficiency. And the other thing we're going to hit heavy on today is system resolution. And there is energy resolution, temporal resolution, and then spatial resolution. So we'll talk a little bit about principles on several of on those right now. So detector efficiency or sensitivity. Detector efficiency is the ratio of the number of detected events to the number of available events, meaning that radiation is coming off of some source, whether that's our patient or something else that we're measuring. That radiation comes off 360 degrees from that source, and there's a certain amount of it. So sensitivity or efficiency is saying, of all of that that's coming off, how much are we able to gather with our instrument and measure and detect? Okay, how efficient or sensitive are we? Can we grab all of that information coming off? So geometric efficiency, when we say that, what we're meaning is we have to be able to, radiation has to hit our instrument, right? So there's a certain amount of placement and how's it placed. That's geometric. Intrinsic efficiency is, can we get the energy deposited through interaction? Can we detect energy? Can we know what type of energy? And then photo peak is can we detect what type of energy we're looking at? So I-131, TEC, the different types of energy, okay? So that geometric is mostly affected. The biggest thing that affects it is source to detector distance, right? So if I have my camera or I have a probe or anything else, and I have it close to my source, which often is our patient, we're going to be able to see and gather a greater amount than if we move it further. Why? Because radiation spreads and goes in 360 degrees. So if we're very close, we're gathering a lot, everything that's coming off. If we're farther away, we're missing some of it shooting off into space. Okay, so it's just basic, like a geometric efficiency is the closer we are, the more efficient we are. Now, the things that really make a difference here is detector configuration, meaning like the size and the shape and the type of thing we're detecting with. Do we have one flat surface we're detecting with, or is it something that surrounds the radiation source? A good example of that, and we'll talk about this in the next lecture, is a well counter. A well counter, you drop your radiation source down inside of it, and it's almost completely surrounded, right? So you're going to have really good efficiency and sensitivity versus your camera is just one flat, one plane, one direction. Okay, so the size and shape of things matters in our efficiency. So in that intrinsic efficiency, again, this is the fraction of the gamma photons that are able to be absorbed by our detector or in the equipment. So this is going to have to do with things like the energy of the photon being looked at. So depending on if we're using I-131 or TEC, this is going to be the detector type or the composition of the detector. So this would be things like the thickness of the detector, the type of material that the detector is made out of. We have something called an attenuation coefficient. So in other words, the more thick something is, or the higher density that something is, the more ability it has to stop radiation and be able to measure it. We have to be able to stop X-rays to be able to measure them. So if you think about low energy photons, something that is like, say, like TeC, which is like 140 keV, that isn't as strong as something like I-131, who's like 364, right? So if we have a material that is less dense, it might be able to stop TeC, but it might not stop I-131. And if we can't stop something, we can't measure it. Let me show you a principle really quick that you need to understand why that works. And that is the photoelectric effect. We talked a little bit about the photoelectric effect last time. And we mentioned, remember, that the photoelectric effect is when an incoming photon comes into a nuclide, strikes a K-shell, the K-shell is ejected, we get some characteristic X-ray. But the important thing that I asked last time is what happens to this incoming photon? That's the most important thing, is that it's absorbed, okay? When we are doing nuclear medicine, in order to measure something, we want the photoelectric effect, because if we can completely absorb a photon, then we can measure it accurately. If it comes in and has more of like a Compton scatter effect or something else, goes off into la la land, well, we didn't get a good measure. We can't measure that. We can only measure something that we absorb. So we want the photoelectric effect to happen. Okay, we want that absorption. That's the only way. That's what we're really talking about when we're talking about intrinsic efficiency, is can that material that we're using in our camera absorb it so that it can be measured. Okay. And the last one is photopeak, and that's just the ability of your detector or your equipment to discriminate the type of energy it's seeing. In other words, between like I-131 and TeC and things like that. And we'll talk and define that obviously more as we go along as well. Okay, so that's kind of the components of the efficiency or the sensitivity. Now we're going to talk about kind of general principles about resolution. Okay, so the first one is energy resolution. Energy resolution allows the discrimination of photoelectric event versus scatter, right? So can my camera see a true event and be able to disregard any other type of radiation it sees, any type of scatter or any other weirdness that's happened? Can I resolve the energy and look for what I'm trying to look for? Okay. In an ideal detector, all electronic pulses would result from complete absorption of a specific photon. The amplitude of electronic signal that we get in our equipment eventually reflects the energy absorbed. So whatever is coming in, we need to be able to measure it by photoelectric, not have anything else going on in here, and be able to then get to the point where we can identify what we see in an electronic pulse. And we'll walk through that later as well. So again, some of this might feel convoluted. We'll talk about full width half max and how we measure energy resolution with that. Don't worry about it right now, we'll get there. The other one is temporal resolution, and that's the ability to be able to take a signal, a energy signal or a photon, and then be able to completely change that to an electrical impulse that we use by the time we have our camera and our computer putting an image on the screen, right? So we can go from a photon all the way to an electrical signal. That is our temporal resolution. When you talk about temporal resolution, you can have something called dead time. And we'll refer to dead time a little more when we talk about the principles with well counters and some of these other things. But essentially, dead time is the amount of time from when the photon strikes your detection equipment to the time that you can get that electrical signal. There's a finite time for that process to take place, and that's dead time. And there's two types. One is non-parallelizable, okay? In non-parallelizable, an event happens and it completely finishes the process before the equipment will see a new event and record the process. So it sees something, completes it, sees something, completes it. And when we're talking about dead time, these are like nanoseconds. So it's not like this takes a long time. These aren't recognizably noticeable, but it'll happen and then it completes the process. In parallelizable, the system, it needs uninterrupted processing time. So it sees an event and it tries to finish an event, but if another if another detection of radiation happens, then instead of completing the first event, it goes back and tries to start that event again. And so you'll see this in systems where if we have too much radiation, and we'll talk about it later, it can overwhelm the system to where the system shuts down. So that's what's called paralyzable. And we'll talk more about those when we talk about detection equipment in terms of other things other than a gamma camera, but it can apply here. So that's temporal resolution. Today, I want you to think about temporal resolution as I started as a photon, I get to an electrical signal. That's a temporal. Can we do that accurately? Temporal resolution. And then spatial resolution is the system's ability to demonstrate detail, the system's ability to accurately represent where a radioactive event occurred. In this case, since we're talking about a camera array within the body, can we actually represent where that radiation that we detected occurred in time and space? We'll also talk about the principle of full width half max for spatial resolution. And again, we'll get to that. Don't stress about it right now. Okay, so that's some general principles, and I know they were convoluted, and you might be like, I don't even know for sure what he was talking about, but don't worry about that right now. As we're going through the camera now, we'll reference back, and they'll make a lot more sense. When you're going back and studying this, I want you to go through those basic principles because it's good to understand them. But again, you'll understand them better as we go through with the camera as well. Okay, so gamma cameras, they are originally called Anger cameras, and nobody calls them an Anger camera anymore, but you may hear that in a textbook, or you could see it on a test question or something, possibly on your boards. Probably not, but it's good to know that when someone says an Anger camera, they're simply just talking about a gamma camera. Anger was one of the early developers of the gamma camera scientist. Last name was Anger, so it initially got called Anger camera, eventually then converted to being mostly called gamma camera. So you might see that. We're going to talk about modern gamma cameras today. We won't get into like history of old ones much. The basic technology really hasn't changed a lot. And then we'll also talk, I may mention the semiconductor detectors in a brief way, you'll see, but you really probably won't see testing on that. It's in your book, and I would of course recommend just reading what a semiconductor detector is, but your really focus is going to be on the main gamma camera and how that works, and that's what you're going to see in testing. So all right, before we jump in, I want to, and let me say this first. What we're going to do here is we're going to start, I found the easiest way to teach this is to start from the source, which is your patient. And we're going to start with those photons traveling out of your patient. And then we're going to go through the camera from starting at the collimators, through the crystal, through the photomultiplier tubes. We're going to go through the basic process of the signal that the signal travels to eventually get a pixel on your screen. Okay, that's the path we're going to take here. Before we do that, we need to be reminded of some basic radiation principles that are important. You remember in our first lecture, I showed this sinusoidal pattern of energy, right? And we talked about how we see visible light, and that by the time we get up to X-rays and gamma rays, we have a lot more frequency and intensity. They're a lot stronger, and they're tightly, that wave is so tight together that I mentioned before that we call it a photon, as if it has mass, but it does not. It's energy. So today when we talk, I'm going to say photon a lot, right? We're really just talking about energy, but we're talking about those tight packets of energy. And to understand the physics of nuclear medicine, you really almost have to refer to it as though it's a thing that has mass. But just remember, as we're talking here, when we talk about photons, they are energy, they don't have mass, and that will help our understanding. The other really important thing to understand is how do photons travel? And what I mean by that is, remember, when you have a radioactive source, it is giving off radiation in 360 degrees, right? I guess cubed, however you would say that, but in all directions, okay? Radiation is going off in all directions. So as we start to talk about the camera, when we talk about how photons are traveling, it helps to remember that, again, photons are energy, and that then they travel in all directions from the radioactive source, which in this case, talking about a camera, is going to be our patient. All right. So we're going to start out with collimators. Collimators is the first thing that our photons are going to interact with on our camera once they've left the patient. So the main purpose of a collimator is to define the field of view and to reject unwanted photons. Now, before we get too far on this, I know you, especially those of you in X-ray, which are many of you, I've heard the word collimators before. I need you to forget what an X-ray collimator is. There are some similarities, but there are major differences that matter. Also, the collimators in an X-ray help with image production, but the collimators in Nuke Med are probably the primary thing that is responsible for forming our image. So they're very different. They're called the same thing, some similarities, but just remember to not get your brain too confused, okay? So define the field of view, define what we're able to look at, and then reject unwanted photons. Huge. That's probably I probably should have put that one as number 1, reject unwanted photons, okay? Collimators are the image forming aperture of the gamma camera. They're made from materials with high atomic number, so high Z number, okay? So they're dense. Usually that's lead or tungsten. In the collimators, you're going to have boreholes between lead walls called septa. So we're going to talk about boreholes today. We're going to talk about septa and what those do. You might call this selective absorption. What a collimator does is it makes it so that only photons traveling parallel to the septa are able to reach inside the camera, able to get to our detection equipment, okay? Now I want you to look, right here is what an actual collimator looks. Now obviously this is just a little section of a collimator. A collimator covers your entire head of your camera in both directions. It covers the entire thing. So this is just a little section, but notice there's these boreholes surrounded by septa. So that's what you're seeing here, the holes and the septa, okay? Now, on this first graphic, remember, radiation is going off in all directions. So we're going to point out some letters here, like, for example, if you look at D, this represents one photon that is coming off, going straight up towards the camera. Realize that D has many photons going all over the place, right? In this case, we're going to analyze this one photon coming straight up. What you'll notice is that this photon is traveling parallel to the septa. And because of that, it goes right in between the septa and it comes and it hits the crystal, which we'll talk about in a minute, to start forming our image. Now, what we want is we want these events or these photons, we want parallel photons to be captured. And the reason is because this camera head is going to represent exactly what it sees on the body. If radiation is happening here in the body and I want to image it, the only way I can accurately record it is if I put it exactly above where it is on my camera in time, or excuse me, in space, right? It has to be represented exactly above where it is to get a good image. Because as you can imagine, let's come over to B. And you can imagine D is going in all different directions. We only want what goes straight. If we look at B, we notice that it's traveling at kind of an angle to the right here. And what you'll notice happens is that as it comes up and travels to an angle, it contacts one of the septa and that septa blocks it. And that is what we want because we only want parallel photons being accepted by the camera because a parallel photon will accurately represent on our camera where it is in space on the patient, okay? So that's what it's doing. It's getting rid of anything we don't want to see and only accepting parallel events, which is what we want to see, okay? So that's what you'll notice on this first one. Let me give you, and this is interesting, you guys, less than 0.1% of gamma rays that come off of a patient actually make it to the detector, which is weird. That seems like a very inefficient system, and it sort of is, but we have to do it that way because only parallel events will represent resolution in time and space, okay? Really in space, not quite so time. Let me give you kind of, here's a more accurate representation of what something might look like, right? So I tried to show photons going off in all kinds of crazy directions here, okay? What I want you to notice is that the ones that are more parallel are the ones that are making it through the septa. Now, one thing I want you to pay attention to here is you'll notice, for example, let's say this one over here, it's not perfectly parallel. It's actually slightly at an angle. We're going to talk about borehole size and what difference that makes. But you'll notice that it's a slightly at an angle, okay? This is something in nuclear medicine that we just have to accept because we have to let some of that information through and we have to reject others. Not everything is going to be perfectly parallel because remember, a photon is infinitely small in size, doesn't have mass, right? So we're letting a bit of energy through at different directions, but we're trying to cut off the ones that are really badly angled because we don't want our image represented in the wrong place. If I had a photon that came off here on me, and I accepted the one that went clear over here, it would make it look like this anatomy is over here on my picture. We want that anatomy to be represented exactly where it is when it hits the detector, okay? All right, so let's talk about sensitivity because collimators affect the sensitivity of the camera. Just like I mentioned a minute ago, less than 0.1% of gamma rays make it. And remember, we talked about in principles a minute ago that sensitivity is of all the radiation coming off, how much of it am I gathering, right? The more I'm able to gather, the more sensitive I am, the camera is. So here's what affects sensitivity. Again, it's the number of counts the camera receives per minute per microcurie of activity. Don't stress about knowing per minute per microcurie. Just understand the principle that of the source of radiation coming off, how much of it can I gather? Okay, what's that? I put that in parentheses. What's available versus what do I get? That's sensitivity. So collimator sensitivity is affected by borehole diameter, septal thickness, and borehole length. So let me try to explain each one of those. As you can imagine, if we go back to our picture of the boreholes, okay, if you think of photons traveling through these holes to get to the camera, what you might imagine is that if I take that hole and I make that hole much bigger, more radiation is now going to get through, right? So when we increase our borehole size, we increase sensitivity. When we make our borehole size smaller, we reduce sensitivity, okay? Because again, bigger holes can gather more. Septal thickness. If you go back to this picture, if we left these boreholes the same size, but we made our septa thicker, we're making it so that there's less boreholes across the image. So we're going to be gathering less data, so sensitivity goes down. So when septa are thin, we're more sensitive. When septa are thick, we're less sensitive, okay? The last one is borehole length, okay? And let me see if I have, yeah, borehole length. So I'm gonna go to, let's go to this picture again. Remember I said that perfectly parallel ones, so there's this photon coming through here. This thing's like perfectly parallel to those that's coming through. And I mentioned that ones, let's take a look at this one. You'll see that this one is angled slightly. And so it kind of barely made it through. This is another one to look at that's angled, right? So it enters in right in the middle of the two septa and it angles and it barely makes it through to the camera. What I want you to do is imagine what would happen if we took on this photon and we made those septa or the boreholes, everything longer. So if we made that longer and we continued this line, and let's say our septa went clear up here, eventually the angle of that, even though it's slight, would hit the septa. So that means that longer boreholes are going to be let less through. It's more likely that an angled photon will hit that septa. So the longer we make our boreholes, the less sensitive we're going to be on our camera. Okay, so shorter borehole length is going to be more sensitive. Okay, so again, I'm just going to repeat this one more time. Well, actually, let's read this here. So shorter borehole length and larger borehole diameter yield greater sensitivity because more photons are able to pass through the collimator. Okay, now we need to go and talk about resolution, and then we're going to connect these two principles because they affect each other. Okay, so collimator resolution is perpendicular photons give the best resolution. Why? Because if it's perfectly at 90 degrees, then it represents the radiation that happened in the body part exactly where it happened, right? So perpendicular events, they give us the greatest resolution because they represent where it originated. So non-perpendicular photons are slightly moved or slightly misrepresented. So in nuclear medicine, you've probably noticed that when you look at a CT scan, right, that you have these really good edges and it looks really pretty. Or you look at an MRI and you notice that when you look at nuke med, it almost looks like kind of fuzzy. Like I've heard doctors call it unclear medicine instead of nuclear medicine, right? Because we're slightly blurred. The reason for that is the best you can get on a gamma camera is about a 3 to 4 millimeter resolution. And the reason is that if we make our boreholes too small, then we're letting nothing through, right? We have to let enough through that we get some angled things. Okay, so that's kind of resolution is how much of that angle we allow through. So let's talk about then the principles that affect that. So borehole length affects resolution. I mentioned a minute ago, and we'll go back. If I have shorter boreholes, the sensitivity goes up, but again, I'm going to have to allow things that are at a greater angle get through a shorter borehole, right? Things when the borehole's really long, then man, that thing has to be perpendicular. If it's slightly off at an angle, it's going to hit the septa. But perpendicular increases resolution, right? That's why borehole length, when we have longer borehole lengths, we get better resolution because those perpendicular photons get through. Borehole diameter, same thing. If we increase the diameter of the hole, we're going to allow more photons to get through, but that allows a greater angle of photon to get through. If we make our borehole smaller, then only photons that are traveling at that perfect 90-degree or close to it get through, okay? So, and then the other one is distance, and I'll show you a graphic for that one. But borehole length, borehole diameter are going to, borehole length, when we make it longer, better resolution. When we make the diameter of the borehole smaller, better resolution, okay? Let me show you, the picture is better to understand distance. So let's look at that real quick. So on this picture right here, so longer length boreholes give better spatial resolution because they limit those non-perpendicular photons. And then longer length boreholes decrease sensitivity because more photons are blocked. This is a great graphic to show that. What I've done is I tried to line up these cameras exactly at the same spot. And then what I did is I lined up the source, or the radiation source, at exactly the same spot. So those are equidistant. The camera to the source is exactly the same. This is what I want you to notice. And the fan pattern of this radiation that I've demonstrated here, it's the same fan pattern. So over here you have the shorter septa, right? And as you can see, almost every one of these photons is getting through, even the ones that are fairly angled. This one looks like it's probably hitting, but the rest of these are getting through, right? What happens when I just simply extend the length of the boreholes in the septa? Well, that's what's happening over here. So I've extended the length, and you'll notice that because of that length extension, I'm now blocking and cutting off a bunch of these photons that are not perpendicular, which is what I want, okay? What you notice here, though, is that over here, more photons got through, over here, less got through. Now, hopefully you're starting to put together in your mind that sensitivity and resolution battle between each other. They have an inverse relationship, okay? When we do things that increase sensitivity and allow more photons in, we're usually reducing the resolution, right? And when we try to increase resolution, we have to account for the fact that, hey, we're going to get less photons because we're only accepting those ones that are perfect, okay? So there's an inverse relationship between resolution and sensitivity. It's a battle that we have in nuke med, but it's a battle we have to do because this is what we have to do to get our images through these collimators. That's why I say these are the main image part of a gamma camera, really. These collimators are what allow the image formation to really take place. So again, I've kind of summed that up here. Collimator resolution versus sensitivity. Sensitivity can be increased by increasing borehole size and decreasing borehole length. And resolution can be increased by a smaller borehole size and an increased borehole length. They have that opposite of effect on each other, okay? All right, so the last thing I want to talk about is distance. Distance is the other major effect besides the sensitivity and the resolution and how those work. Distance is a huge thing. So this is similar. Realize that these are the exact same collimators, the boreholes and everything are exactly the same. All I'm doing is changing the distance that my radiation source is from the detector. And this is kind of what I mentioned when I was talking about the first principles at the beginning, right? So you'll notice that if I have a source that's backed way away from my detector, that yes, I have angled, everything going off in 360 angles. And you'll notice that because of the relationship and the distance, that some of these are making it through the septa. In fact, all of these are making it through, right? Whereas if I simply decrease the distance, okay, I decrease that distance, then I'm cutting off those unwanted photons. Now, the thing to understand about distance is that it always increases resolution to get closer. Get that in your head, it'll make you a good tech. Get the camera close to your patient. I understand that patients have claustrophobia, there's issues, there's reasons why you can't get it close. But the principle you're going on here is the reason why you're getting it close is you're going to increase your resolution by a ton. It's super important to get your camera head as close to the radiation source as possible, and this is why. Now, the other cool thing is that you don't actually get the inverse relationship here, because when you're farther away from a source, remember, radiation goes in 360, right? So half of that source is going off into la la land when your detector's way out here. When you bring that detector closer, you're gathering more of it, even though you're cutting some of it off with your detectors and you're getting rid of the angled ones, you're still gathering more. So distance, shorter distance increases sensitivity and resolution. That's the principle that does both. This is why you need to have your camera close. This is a thing that I've noticed with techs that I work with and stuff that people just kind of, I don't know if we get lazy about and forget. I probably even have been guilty of that a few times, but this is why you get your camera close to your patient, because your sensitivity and your resolution, the two things we want out of nuclear medicine, go up, up, up. Okay. This is a graphic I found that just kind of shows that and we're going to talk about different types of collimator heads. And so it shows us some of those, and it kind of gives the resolution. But what I liked about this is it shows that when we increase, this is increasing the distance, resolution always goes down no matter what kind of collimator you're using, no matter what your camera is doing. If you increase distance, resolution goes down. If you get distance short, resolution goes up. Okay, so now we're going to talk about types of collimators. That's the general principle of collimators. That's how they work. That's why they form the images. Now we're going to talk about collimator types or classifications. So most of your cameras will come with, and not all of them, it depends on what you do in your department, but kind of a general, what you'll see on most gamma cameras is there's 3 energy level types of collimators. You have high energy collimators, medium energy collimators, and low energy collimators, okay? The main difference is that makes these collimators different is simply septal thickness, okay? So you'll notice up here, I listed some KeV ranges and some types of nuclides that use these. So I put I-131, this has a range of like 300 to 400. So anything that's up in that level, like I-131 is like 364, I think it is. It's going to be up in that range. Medium energy range like gallium, indium, low energy range, of course, is our tech. The main difference is that septal thickness. And the reason why the septum have to be thicker on a higher energy is because it's higher energy, right? A more powerful photon, if we have a really, really thin septum and it's maybe made of lead, but it's really thin, there's the chances that a high energy photon will simply just penetrate that is high, right? So when we're working with higher energy, we have to make it thicker. It's what I mentioned, one of the principles at the beginning is we have to have a high Z number to stop what we want to stop, right? And the whole principle of a collimator working is the ability of those septa to be able to stop unwanted photons. So if you have a high energy photon and your septa is too thin, it's going to blow right through it, or it's going to hit it and cause a bunch of scatter and issues and problems. You're going to get all kinds of radiation everywhere. So again, remember the main difference when you're looking at those collimator differences, the energies, is that you're going to have different septal thicknesses, okay? What else did I want to mention? Oh yeah, that's the other one you should mention here is, as you can imagine from the principles you just learned about collimators, the higher energy the collimator is, it's usually less sensitive. Why? Because we've made those bores thicker, which means the holes ended up getting smaller, or there's less of them to go around. And so sensitivity goes down because you're getting less radiation through to your camera, okay? So less sensitive. Also, there's something called, I asked the question down here, what's septal penetration or crosstalk? That's just when a high energy photon is able to go through that septum and either interact with the septum or cause scatter or just blow right through it. And that's not good for system resolution and for detail. Again, that's kind of what they call it. You may not hear it called that way. When I went through the program, I did get a question like that on the boards, like what is septal penetration or crosstalk? I don't hear many techs talk about that or make that a thing, but kind of generally understand that it could be called septal penetration or crosstalk, and that's all it is. It's when you have a septum that's too small and you get stuff blowing through or causing scatter. All right, let's talk about the types. We're going to reference parallel hole collimators, which is what we've been talking about this whole time. Those are parallel hole. There's also diverging hole collimators, converging hole collimators, and pinhole. And so those are the 4 that we're going to kind of mention today. And again, I won't go over parallel because I just took the last 20 minutes explaining that. But diverging collimators are where they basically take the septa and they fan them outward at an angle. Now you might be saying to yourself, after all I just taught you, like, why in the world would they do that, right? Because it's going opposite of everything. It seems like everything would hit. What this is designed for, and usually you see this in small clinics. I've seen a lot of small heart clinics that have a type of camera where you sit up and it's a really small head. Most of the departments and hospitals have a big head that covers the whole body. If you have a smaller camera head with a big object below, what's happening is, remember, because radiation goes in 360, let's say my picture here where it says object, let's say that this is a much wider, like it went clear out to here, and it went clear out to the right. So it's a really big object. If you allow the detector to see the radiation coming at those angles, and then you slowly go in, what happens is you're able to look at a big body part on a small detector. Okay, a big body part on a small detector. What does happen though is, because you're projecting everything inward, you get a minified view of the organ. And this is a reduction in sensitivity. Okay, so I doubt whether you see a diverging collimator anywhere where you work. If you work in a really small department, it's a possibility you could have them. I don't see these. I've never seen one. Like I said, I've known of some clinics that have maybe used them. You probably won't see this, but it probably will be on your boards to understand what one is. Okay. The other one is a converging collimator, and this is basically the opposite of the first one in every way. So this is designed for imaging small organ parts, or honing down in on a smaller organ like a heart or the brain. And this projects a magnified view. Now, this one increases sensitivity. And the reason being, remember I said radiation goes in 360, right? So it goes out like a fan. You'll notice that on this one, the boreholes and septa are almost matching that 360-degree pattern that there would be. Okay, what happens with this one is you increase sensitivity because you're gathering a lot of photons over a singular small source. So that increases sensitivity, but this gives you a magnified view. So it's opposite of the diverging. Diverging gives you a minified view. This gives you a magnified view. This one, we actually have a camera in our department that does this. Our camera that we do our SPECT hearts on, it has one that's in what we call a pyramid shape, meaning that all 4 ways are kind of honing into a central point. And when we do our SPECT scans, our software allows us to kind of aim that central point right at the heart. And then as it goes around, it gives us a little bit of a magnified, more sensitive view of the heart. And so we do use one of these. They can be in like a fan beam pattern, meaning that across your whole collimator, it all fans out in one direction, or it can be the pyramid, which is like what we have, where it fans in both directions into a central point. But all of those are converging collimators. For this one, good thing to remember is, again, it's magnified view, and that it actually is more increasing in sensitivity, and it's going to be imaging smaller things. Okay. And then the last one is the pinhole collimator. This is designed for really small organs, such as thyroid or like bony joints. Like I've seen people do naviculars with these. Thyroids are done with them a lot. So this really only has 2 septa, and this might seem weird in your brain from everything we've discussed, but essentially these 2 sidewalls are considered the septa. They're usually made out of something with high attenuation like tungsten, so that nothing gets let in. The principle or reason why these work is that the tip of this collimator is usually a little tungsten unit that can be removed, and there's little sizes anywhere from like 3 to 6 millimeters. So the hole that is letting in radiation is tiny, 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 tiny. So this really magnifies down on a small part, like I said, like the navicular or like the thyroid. You're going to get it really close. Again, sensitivity is really reduced because, as you can imagine, you're not getting a whole lot through that little 3 millimeter hole. However, it really magnifies the object. Okay, so the resolution is actually really good. And essentially, every photon is going at angle and all the photons are gathered, but because you're only covering this little minute 3 millimeters, which is basically the size of one borehole, that object is still represented. It's actually flipped. It flips your object from what it looks like. Most of your cameras will correct for that, but it's going to magnify it and flip it. So the thing I want you to remember here is really detailed imaging and really magnified imaging and of very, very small parts. Okay. All right. So that's the collimator. Okay, so the first thing that I said we interacted with is our collimator. The next thing that is right behind the collimator is the crystal. Okay, so we're going to talk about scintillation. I want to talk about scintillation as a general principle and have that kind of flow into us specifically talking about the crystal. But I would first want you to understand, what is scintillation? When I say scintillation, what does that mean? Scintillation is, well, you could view it as a type of energy transfer in which we are able to take a photon and convert that photon into light. That's scintillation, converting a photon into light. Okay. So a scintillation crystal in this case is just converting gamma rays into visible light, what we're looking at. Scintillation crystals using gamma cameras are sodium iodide, and they're called thallium activated sodium iodide, and I'll explain better that in just a minute. Most gamma cameras are about 1/4 inch to 1/2 inch thick, and they cover your entire camera head. So when I was learning about this, for whatever reason, I thought we're going to talk about photomultiplier tubes, and I thought each tube had a little crystal on top of it. No, your whole head is one crystal, one solid crystal, again, about 1/2 inch thick. So it's going to be a big square that sits right on the head of your camera. Okay, that's your crystal. And that's what has that interaction to cause light. Okay. They are hermetically sealed in a reflective material for 2 reasons. One, reflective material, because now we're going to change those photons into light, and we want to measure that light, because eventually we're going to turn it into an electrical signal. So we seal it in a reflective material so we don't lose any of the light. We want to be able to measure it all. And then the second reason that it's sealed is because it's hygroscopic, which means water loving or water absorbing. That the sodium iodide crystal will absorb water from the air. Okay, so it has to be sealed. If it's not sealed, it gets unsealed, it absorbs water, and it loses some of its effectiveness and ability to be able to scintillate or make light. Okay, so it has to be sealed. They're also heat and cold sensitive. It's one of the reasons your camera rooms, they keep track of temperature and things in your camera rooms, because if they get too hot, they can malfunction. If they get too cold, they can malfunction. So they need to be kind of just right. Okay, so that's kind of what it does. Let me say it this way to kind of overarching say that. This is what I would say, what you need to understand about scintillation. When exposed to photons, in this case gamma rays, the crystal gets excited. Okay, I'll say the electrons within the crystal get excited, and to get back to a stable state, they release that excited energy in the form of light. That's the extent to which you need to really understand. I'm going to give you the physics now. This is not going to be a physics that comes on your boards, but it's going to help you understand what's occurring in scintillation. Okay. I also want you to remember, because I'm going to teach you now what thallium activated means, so I guarantee that will be a test. Like, what does the thallium do in a crystal? What's the purpose of it? So here's how this works. Okay. When we've talked about physics up to this point, and we've talked about electrons, we've actually talked about them physically where they're located, like the K shell, and they're located around the nucleus and they're interacting. I'm going to mention electrons. I'm not, and I'm going to talk about them moving. I'm not talking about moving physically. I'm talking about their energy state. So as I have this quick little discussion, just remember, I'm talking about energy levels, not actual places that electrons are going. Okay. So on this chart, any solid material has what's called a valence band and a conduction band. Over on the left, I mentioned these are energy states. Okay, so in the valence band, that's where electrons are at their resting energy level. Okay, and then a conduction band is where they go up into an excited energy level. Okay, so what happens is when a gamma ray, or really any photon, but in this case we're talking about gamma rays, when it strikes the crystal, which is this solid material, the electrons within the crystal get excited and they move from the valence band to the conduction band. When I say move, I don't like using that. I'm not talking about they didn't go anywhere. They just excited and leveled. They moved into that band. That's the way physics says it. But essentially, they got more excited, right? And they moved up into this conduction band. In a pure crystal, they would move up into this conduction band, and then when they get unexcited, they lower back down. In a pure crystal, that's what happens. What they do is they add an impurity to the crystal, which is thallium. That's what we call thallium activated. What the thallium does is it makes it so that when they're lying in the valence band and their photon comes in and they get excited in energy, instead of jumping to the conduction band or that energy level, it holds their energy into what they call the forbidden gap. I don't know why it's named that. I wouldn't have named it that way. These are weird names, but just understand that it doesn't quite go up to that normal excitation of the conduction band. What happens is it goes into this weird middle place where they get less excited because of that thallium. And what happens then is that when they've gotten to that excited state and then they calm down, the way the energy released is in visible light. So without the sodium or the thallium in the sodium iodide crystal, we wouldn't see that. The energy would come off in some other form. In this case, adding a little bit of thallium to a sodium iodide crystal makes it so the energy jumps into the forbidden gap and then releases as light energy. And that's what you see here, is that it comes out as a light photon, right? So we're talking about gamma photons, which are energy. Now we've changed, and now we're talking about light, which is less on that energy spectrum, but it's still energy. We're still going to call it a photon, but it's in the form of light. It's in something that we could see. If we were witnessing X-rays hit these crystals that are sodium activated, we would see them light up. It's visible light, okay? So that's how that works. And again, all I really want you to remember is that they go to an excited state and they come back down and release light. The reason it works in a sodium iodide crystal is because it's doped with thallium. So thallium activated sodium iodide crystal. That's what's happening there. Okay. Couple other principles to realize when this occurs. The higher the gamma photon energy, the more visible light is emitted. What do I mean by that? It means that nuclides that have a higher keV are going to release more light. Okay, so again, TeC at 140, I wrote this in a bullet point down here, but TeC at 140 releases about 3,000 visible light photons. If you were talking about I-131 or indium-111, it would be more than that because they have a higher keV, right? So this is really important because remember, when we talked about the energy resolution of your camera, the ability to go from a photon all the way to an electrical signal, we want that signal to keep its proportionality along that whole thing. Why? Because what are we trying to do with radiation detection equipment? Measure it. To accurately measure it, this has to stay the same. So it's important that 140 keV give 3,000 and we can measure it. And that's what we're trying to do, right? So just remember that the light emitted is proportional to the energy of the photon that interacted with the crystal. This is why, and there's more steps to this. This is why we can start seeing how, oh, I can look at energy and I on a camera and I can say if it's I-131 or if I can say if it's TeC or I can say if it's rubidium, whatever. Well, not rubidium. You wouldn't detect rubidium with a gamma camera. That's a PET scanner. Sorry. We confuse you all. All right. So that's the principle to understand there. Now we're going to move on to the photomultiplier tube. Okay. So again, to give you kind of the stage, we have our collimator. Right after the collimator is our crystal. And then right after the crystal are our photomultiplier tubes. Okay. Photomultiplier tubes, their purpose is they can convert light into an electrical pulse. They convert light into an electrical pulse. Okay. They determine the energy of the incident photon because they can see how much light is there. And then they're also going to determine the location or the XY coordinate of where the event happened on the crystal itself. I won't talk about that right at this moment. We'll talk about how that works in just a second, but they are able to say where the radiation, where the photon hit the crystal, okay? They also record, because again, of how it can keep proportionally see how much light, they record the intensity of that photon that hit, okay? So they were location and intensity, convert that all to an electrical signal. Okay, this is what a photomultiplier tube looks like. Okay. And essentially, I'll kind of walk you through this, but you have a cathode and an anode. So the cathode end is here, anode end is here. You have a photoelectric, or excuse me, that's not what I meant to say. You have a thin photosensitive alloy, a type of metal that's sensitive to light that's on the end here. And then as you come through, you're going to have what are called dinodes and eventually reaching the anode. So here's how this works. An electron that comes off, or excuse me, the light photon that comes off the crystal is going to strike this photosensitive photocathode. When it does, it actually kicks an electron off of this cathode. So now we have an electron popping off. Now, because we have a photocathode and an anode, we have a potential, electric potential, which means there's a pull across there, right? We've created a voltage across there, so there's a pull from one end to the other. So what will happen is that electron is going to be pulled toward the first dynode. Now, there are many dinodes that are lined up in a pattern inside the photomultiplier tube, okay? What happens is it's pulled by that voltage toward the first dynode. It strikes that dynode, and for every one electron that struck that dynode, it kicks off of the dynode about 3 or 4 electrons released. Okay, so now you've hit this first dynode, and then it's attracted, and you'll notice these dynodes are curved to aim and face toward each other. So it strikes the first dynode. 1 electron then becomes 4 electrons. It hits the next one, 4 electrons, then becomes 16 electrons, and it builds, right? And every time it strikes a dynode, you get more and more and more and more and more electrons until it eventually comes and hits the anode side. When it hits the anode side, there's enough electrons produced that you get an electronic pulse. Okay. Those dinodes are repeated. It's about, depending on the type of photomultiplier you have too, this could be like 8 to 14 dinodes that are in here that are producing that amplification of electrons. The electronic pulse is greater, it's been magnified, but it's still proportional to the amount of light that it saw. Okay, so that visible amount of light is now on the other end turned into an electric pulse, and we're going to talk about that pulse that we can measure, and again, it's proportional. So this slide, and I won't really go over the slide. This is basically what I just told you as I looked at the picture, right? And you can go back and look at that, but that's going to walk you through that process of that happening. Now, I actually found a really cool video. Sometimes this video works really well online in lectures, and sometimes it doesn't. And if you're watching on your phone, it's probably going to be really hard to see, but you can watch it later. But this is an animation that I found online that walks you through the moment that visible light kicks off a photon from the photocathode and then goes through this whole process. So I'm just going to play this. Hopefully you can see it. If not, like I said, you can watch it later, but it's pretty cool. So there's the photocathode right here at the beginning, kind of this silver goldy color. Light struck it, electron gets freed. It's cruising, it's going to hit the first dynode, it's multiplied. They did 2, I don't know why. But anyway, you'll notice it's multiplying as it's pulled to each dynode by that electric voltage. It's pulled until eventually it comes through, it's the cathode end. Okay, so that's what's happening. It's multiplying those electrons every time it hits. And essentially, it's just getting electrons, enough electrons that equipment can then see a small pulse or a small signal. Okay, so that is the purpose of the photomultiplier tube. Oops. Okay, so photomultipliers tubes, depending on your camera head, what type of camera you have, there can be anywhere from like 35 to 100 PM tubes that are on the back side of your crystal. So this is what it would look like in a camera, right? So the crystal represents the square there. The crystal would sit on top of those photomultiplier tubes, and all those photomultiplier tubes. They're in intimate contact. Usually they use a type of like a grease or electrode grease that helps really seal those together. And it's usually that grace is like a light sensitive as well, so it doesn't degrade the light in any way. But again, those 8 to 14 diodes amplify that current. It usually ends up being about 50 times that create that weak little pulse that we can look at. Current reaching the anode is reported as an electronic pulse. The energy of the electron pulse is termed photo peak. So in other words, how high of energy is that little pulse you see? That's called a photo peak, and we're going to get into more detail on that. Also, again, temperature changes in the clinic can cause drift in the voltage of PM tubes. So you have to watch that. Again, another reason why it's important camera rooms to be in a good temperature, because if you get a swing in your voltage, then that little pulse that we're going to use to start forming images and doing the rest of our process can be degraded, right? So you want that to be accurately represented. So, okay, we're going to talk about now. I mentioned that the photomultiplier tube can tell us where the event took place on the crystal. So here's how this works. Remember, gamma events, we talked about how they spread in all directions. Well, so does light, right? Because they're both energy, there's just a different intensity of energy. So when a photon strikes a crystal, that crystal gives off light in 360 degrees all the way throughout the crystal. Even though if you have your crystal here, even though it happened here in the crystal, it's going to spread light that goes throughout the crystal, right? So what happens is the photomultiplier tube, and maybe I'll go to this picture. Let's say our event or our strike happens right in here. So this photomultiplier tube that's immediately behind where our event took place is going to have the greatest intensity of signal, right? The biggest signal that comes out the other end of the photomultiplier tube. However, because light spread throughout the crystal, again, the light is going to be most intense where it happened, and it's going to be less intense as it moves away from where it actually occurred. So what's happening is, instead of just one photomultiplier tube seeing the event and being like, hey, I got it, guys, I'll record it. No, all the tubes in the head are measuring that pulse, but they're all going to see a slightly diminished intensity of that pulse as it goes away from where the actual event occurred. And so what your camera is doing is it's taking the data from all of the photomultiplier tubes, and it's calculating the intensity and then able to pinpoint right where it happened on your crystal. Okay, so that's called positioning logic. It's able to take and logically figure out from the amplitude of each of the signals for all of the tubes where it happened. Okay. I think, yeah. Oh, and those signals are basically done in like an XY pattern, just like you did when you were in math and you had to graph things in math, right? You had an X and a Y coordinate. I said that backwards. X and Y coordinate, and 0, 0 was right in the middle, right? So same thing with your camera head. The very middle of your crystal is 0, 0, and then you have an X coordinate positive, you have an X coordinate negative, you have a Y coordinate positive and a Y coordinate negative. And so it's basically going to assign the value of where that event took place by measuring the amplitude from all of the tubes. Okay, and it's going to do that. The other thing that it does is it sums all of those together so that it can give you an intensity. It can remain the intensity of light that it saw. I think I also mentioned on here, it's not super important, but some of the newer digital cameras, instead of using all PM tubes, it will go down and just grab like maybe the 6 to 8 tubes that are around the event that occurred. Some cameras work that way. I don't think you're going to be asked that kind of a question on your boards, but some cameras do work slightly different with a few positioning algorithms that are different. But the basic principle is that the photomultiplier tubes are seeing those events and calculating where it's at. All right. So I put this graphic up here to kind of get us back in our head with a picture of where the heck we're at. So we have the collimator out here. We struck the crystal, we went through the photomultiplier tube, and now we have a small signal coming out the other end. I don't really talk about the high voltage power supply. There's power that goes to the PM tubes. It's not super. I don't think you're going to get test questions about that. But what happens is, after the signal comes out of the PM tube, it's going to go through a preamp and then an amplifier. And so we'll mention both of those. So the preamp, basically what it does is it's sitting right on the back of the tube. Every photomultiplier tube has a little preamp right on the back of it. Basically, it just boosts that signal 4 or 5 times. The thing you understand is the PM tube sees a signal, but it's super small and super weak, and it's in a state where trying to then do something with that data is very difficult. So we have to boost the signal. Okay, so it's boosted about 4 or 5 times and it's connected closely. After that, it's going to travel to, the signal is going to travel to a regular amplifier. The regular amplifier, this is where it really boosts it up to a signal that we can actually use. So this is about 8,000 times proportionate to the energy that came out of that PM tube. So this is where it really just boosts that signal up. Again, it keeps it proportional, right? So if a smaller signal came in, it boosts that signal about 8,000 times. If a bigger signal came in off the PM tube, it's going to boost that 8,000 times, so that it remains proportionate, but it's just the amplifier boosts it a lot more. The other thing that an amplifier will do is it will slightly shape the signal just to make the signal look a little bit more uniform. It doesn't shape it a ton, but it just kind of adjusts and makes it more usable for a computer. Both of those still maintain the X and Y positioning and the Z intensity. Okay, the next thing we're going to go to is the pulse height analyzer. Okay, so now that we've created this great signal, and remember I called that a pulse. Now we send it through software that analyzes that pulse and can start to tell us what we're looking at, and do a few things to help clean up our signal. So the basic principle of a pulse height analyzer is to disregard signals from background scatter or anything else, and only see that primary signal from the photon that we're trying to record. We call it a photo peak, and we'll talk about that more in just a second. But the photomultiplier tube can make a discrimination because the energy deposited by a photon bears a linear or proportional relation to the pulse emerging from the PMT. Again, that's another way to say the thing I've been saying the whole time, is just that it's proportional. So the pulse height analyzer can look at it and see what it looks like and determine what isotope or other things that it's looking at. Let me give you a little more explanation. So, we'll talk here and then we'll go to the next slide. I have an actual pulse height for an isotope on the next slide. We'll do this one first. So when you run, your camera will have a spectrogram in it. And you may have seen some of your techs looking at this. If you put a patient under a scanner, you can look at a spectrogram and it will have this pulse like you see here. You'll see this kind of wave, right? You'll see a wave. And basically this is allowing and telling you what type of isotope you have. So along the y-axis, you have the number of pulses that it's seeing. So you have a radiation source on the detector, and what the camera is saying, in other words, how high this peak is, it's saying, hey, I'm seeing a lot of this type of a pulse. I'm seeing a lot of this particular energy of a pulse. And that's what you're seeing, is number of pulses, okay? And then down here, we call it the pulse height, but it's telling you what energy level it's seeing in each pulse. I'm going to come back to this because I almost think it's easier to look at a real isotope. So we'll come back to this window. Let me show you the next one. Okay, so this is the pulse height. This is the spectrogram of cesium-137. So what you're seeing here is, again, the energy or the pulse height, the type of energy. So cesium-137 has a 662 keV that it gives off. So what it's telling you is, again, the number of pulses, is this graph is saying, hey, I'm seeing a lot of stuff at 662. I'm getting a lot of pulses at 662. So what that's telling me is, if I look at this as a tech and I don't know what radiation source I'm looking at, I mean, you're going to know, but if I didn't, I could look at this and be like, hey, I know cesium-137 is 662. I stick this under a spectroscope and I'm like, man, we definitely have cesium in this sample or whatever that we're looking at, right? So it's gonna have that 662. Now, what's interesting here is you notice that the spectrogram is also seeing some other stuff. Okay, we'll talk about that in a minute, but just so you can kind of get the idea that, hey, this one's cesium. I'm seeing a pulse height. My pulse height is kind of telling me what I'm seeing, and then my number of pulses and how many. So let's go back here for a minute to the generic. Okay, so what the discriminator does is it says, I don't want any extra stuff. It's your way of telling your camera, hey, camera, I gave my patient tech, and I really need you to look for tech. I don't want you to see anything else. If there's scatter, if there's other things, there's a certain energy that I'm looking for because I want to produce a good image, and so I need you to see only that material that's coming off the patient, right? So that's what we're doing, is that the pulse height analyzer has a lower level discriminator and an upper level discriminator. And you can see that on the pulse height here, the analyzer, right? So you have a lower level and an upper level. And essentially what you're doing is you're telling your computer, if you see any other energy, I want you to ignore it below this level, and any other energy above this level. And usually we give, it's called a window, right? A photo peak window. So your window is usually set at around 15 to 20% above what you're looking for. So I wrote down here, if I'm looking for 140 kV, which is tech, right? And I just realized I have KVP. See, I find mistakes all the time. KEV, not KVP. You X-ray people, stop cheering. It's not KVP, but 140 KEV. So if I know that, I gave my patient tech, and I'm going to tell my camera, please look for 140, and I'll allow you to have a little bit of wiggle room. I'll give you a 20% window, which means I'm giving you 10% above and 10% below. So in the case of 140, you might have like, what, 155 or something above. It might be allowing that in, and then below, 15 below that, right? So 125 over. So you're going from 125 to 155, and that's how much of that window you're letting in. And you're telling your camera straight up, you might see other things. I don't want you to record them. I want you to ignore those things, right? And so this is what starts to look at, again, our system or our camera resolution. Its ability to be able to take a signal, again, from that photon and now start to produce an electrical signal, but also keep it clean and keep it, this is called energy resolution. We mentioned that at the beginning, energy resolution. Are we able to resolve the resolution that we want to look at and see that peak and see the photon and tell our camera to look for what we want it to look for? That's energy resolution, okay? You can have a symmetric window or an asymmetric window, okay? I'm going to go back to the other picture to explain to you why you would do anything other than symmetric. So this one is symmetric. I've lined it right down the middle. I've got 10 above and 10 below. Asymmetric windows have a purpose. Let me show you on the cesium. So you notice these other things, right? I told you I'd talk about these other things that are going on out here. Like, what are they? These graphics down here represent a crystal with photomultiplier tube and with the septa on the sides of it, right? So in this case, a photon came in and it was total absorption, and we have what we want, and that's beautiful. You can have what's called Compton scatter. You can get Compton scatter if something strikes the crystal and is diverted in Compton scatter and goes and strikes somewhere else. Over here, you can have the lead hit and can give off a little bit of scatter radiation, again, in the form of characteristic X-rays. You can have what's called a coincidence, where two of them hit at the same time and make it look like the pulse is way bigger than it is. So there's other things, that energy levels that can be seen by your camera. That's what's represented all throughout here, okay? Is all those different energy levels. You notice right here, there's this peak, and you're like, hey, what's that? And what happens is that when cesium decays, it decays by internal conversion. Remember, internal conversion is something we don't want. It's where it reaches out and grabs one of those electrons, or excuse me, where there's, I said that backwards. It's giving off intensity, and it strikes some of those outer shells and then causes some characteristic X-rays to come off. Well, cesium-137 has some internal conversion that happens in it. And come to find out, when that internal conversion comes off, it gives off a characteristic X-ray in the form of like barium, right? So you're seeing that come off. That's what you're seeing there. So we don't want any of that for our imaging. We don't want, you also notice this Compton, this represents Compton scatter. It's called the Compton edge and the Compton valley. We don't want any of that. And on some isotopes, especially ones that are high energy, they can get more Compton. And instead of the Compton peak sitting out here, what will happen is you'll see that your peak come down like this, and then all of a sudden it will break off in a big Compton edge right there, right? So it's like this Compton edge that's clear up into here and kind of butting into the signal that you're trying to look at. So if I take an asymmetric window, meaning that I allow a greater amount on the higher energy end of this and less on the lower end, then I can cut out that Compton scatter, which is not helping my image, and mostly keep what I want. So most of the time you're going to see your window symmetric and set right in the middle, but there are times on certain isotopes where you might see that shifted a little bit to cut out some of the Compton and some of those other things that are happening. When you go to your clinicals next, see if your tech, most cameras will, there's a page when you're setting up the patient where you can put them under there, and then you can pull up the spectrography and you can look at this. You can see what peaks you're seeing and you can see how your camera's adjusted for those peaks. So ask your tech to show you that on your camera, okay? So that is the pulse height. And I kind of put, why isn't a photo peak just this perfect straight thing? Why is it kind of a hump or a varied energy? Well, we just explained that because there can be things with the camera, there can be, you know, problems with the crystal, there can be problems with the patient, there can be scatter, there can be attenuation, there can be all kinds of problems to where even though our equipment's running great and we've got good things, that signal is just never going to be a perfect, you know, like Cesium 662. It's going to always be some form of a pulse that has a little bit of breadth of energy. What we want when we talk about energy resolution, we want that breadth to be more narrow. Does that make sense? So if you go back here, we don't want this peak to be a really wide, long peak. We want it to be narrow because that means our camera is resolving the energy. It's seeing the energy we want it to see, and it's able to see that in a small peak. If we get something that's really wide, we're going to be like, something's going on with my camera. Like something's not resolving right. Something's not able to see the energy, and that's wrong. So the way that we have a way of measuring that, and that is what full width half max is. It's our way to measure energy resolution. Okay, so you're not going to have to do one of these problems, but you're going to need to understand that full width half max measures energy and measures the spread of energy. Okay, so I wrote that here, the amount of spread that is manifest in the energy spectrum. What I mean is that pulse, is it narrow or is it widened way out? Okay, again, we want narrow. Okay, so the way that they measure this is called full width half max. And basically what you do is the max of your peak is all the way up, right? So in this case, this peak goes all the way up to number of events, and it's up to 1,000, okay? If we go to half of that, it's 500, okay? So that's the half max part of when we say full width half max. So at the half max, what you do is you measure the width of your energy. So at half of the maximum peak, you measure the width of your energy. In this case, this is going from 132.5, where we first see it, the energy level, and the highest energy level we see at half max is 147.5. So this is the way that you would figure that out. You would essentially take your full width half max, the KeV, and then you would divide it by the photon energy, and you would times that by 100. So that's what I did over here. So you take 147, subtract 132, so that gives us this distance. How many is between that? There's 15 keV there. From 132 to 147, there's 15 keV. So I take that 15 keV, and in this case, we're saying that we're looking at tech. So tech has a 140 keV. So we divided 15 divided by 140. And then we multiply that by 100. So we do that on the calculator, take 15 divided by 140 and multiply it by 100. It's going to give you 10.7, and that's a percentage, 10.7%. So for tech, a good resolution, that's telling you how wide that percentage is going. So if you had something that's like 30%, that means your peak is doing like something like this. But if you have a nice narrow one, like 10%, it's like a nice, good narrow peak. So in this case, we're within 10 to 12% is a good peak for technetium. 7 to 9 is a good one for cesium. So these are different depending on the isotope that you're looking at. You don't need to have those percentages memorized, okay? What I want you to understand is that energy resolution uses full width half max to measure the spread of energy. And I need you to understand that that's what we mean when we say spread of energy. We're talking about that pulse. We're talking about the kind of width or that wideness of the pulse. Again, it's the spread of energy on our energy spectrum. Okay. Now, there's one other time we use full width half max to also look at spatial resolution. And I've taught this a few different times. I'm going to pop out of our discussion about energy and really quickly just show full width half max on spatial resolution. This can feel sort of confusing, but I found that keeping full width half max in one space on the two things you use it for is better. So spatial resolution, when we talk about spatial resolution and we look at a full width half max chart, we're measuring the spread of resolution. Okay, so a gamma camera has an inherent spatial resolution of about 3 millimeters, and that's because of your borehole size, right? You're just not going to get any better than the size of the borehole. What we want to know is, how does your camera resolve resolution and see things between all those boreholes across your whole head? So here's how this works. And this is done usually by like your physicist that comes in. But they have a bar phantom. It's like a long bar, okay? And it's filled with some sort of radioactive source. They place that slightly above your camera head. And as you can imagine, it's giving off radiation in 360 degrees. What your camera should be able to do is record those parallel events coming off that rod. And then anything that's spreading out should obviously have less events recorded as it goes out, right? So what they do is they graph that. They'll go all the way from one end of your camera and say, what kind of intensity do I see over here? All the way up to where the bar phantom is, which they should see high intensity, and then back down the other side. And that's the curve you're seeing here. So this would be the distance. So 0.0 would be right where the bar is hanging over your camera. And then you'd be going like kind of like to the right and to the left, right, in distance. And then they record the count rate. So you end up with a graph. Again, this isn't the energy spread. It's just a graph representing the intensity that your camera sees from that tiny little bar. What we should see is that most of the intensity should be in the middle, and we want to see hardly anything as we go out towards the edges. In fact, the closer that graph becomes, that tells you that your camera has really good resolution because it's only seeing that tiny bar that's sitting above your camera, okay? And so as that graph goes out, we should see less and less. So if your physicist hung up if he hung up that radiation source and he got this graph that was really wide, it means something's going on with my camera because it's seeing radiation way over here at an angle where it shouldn't be. I should only see it right underneath, okay? So they measure that with full width half max in the same way. They say, okay, my count rate, I'll go with half of my count rate, and then I'll measure the width of that spread. And it's just measuring resolution. So just understand that full width half max is really a mathematical principle that they use on a graph, right? We use it to measure our energy resolution by looking at our pulse, and we also use it to measure our spatial resolution looking at intensity across your camera, okay? Hopefully that didn't confuse you too much. Watch it again, but those are two places where you could get questions about full width half max, and you need to pay attention. Am I talking about spatial resolution or am I talking about energy resolution? Okay, so just pay attention to those. And I threw in another one right here, cesium of measurement of full width half max. You can look at that. I won't cover it right now. Okay, so basically, we made it through our collimator, through our crystal, through our photomultiplier tubes. We went through our amplifiers, we went through our pulse height analyzer, and now we're ready to basically make an image. So I'm gonna go through the image display. We have image display left, and then after that we're going to talk about how SPECT works, and then some quality control. We are sitting at 2:23, so again, you guys need to go. I'll keep lecturing, and then you can watch it back later as well. But the image display part should just be a couple of minutes if you want to listen to that, and then go, or whatever you're comfortable with. If you need to go, but please don't miss Sean's class. Go to her class. So again, I'll keep going, and then just come back later and watch. So I mentioned before, again, we have our patient, and we come up through all of the equipment that we talked about. And then remember, I mentioned that we have this XY coordinates with Z intensity, okay? So our image display, the most common way of acquiring on a gamma camera is in what we call matrix mode or frame mode. So matrix is just a parameter that determines the number of pixels that will be used to acquire a study. Now, I need to stop you right there. When I say pixel, you all think of a computer screen. I'm not talking about a computer screen. What I'm talking about is the number of pixel elements that are going to be used to divide your field of view into sections or a graph. Remember, we talked about the XY coordinate. So we call those pixel elements. We're going to divide that whole space up into a certain amount of pixel elements, and we can use different numbers of pixel elements, okay? So that is your matrix. Think of your camera head, not your screen, Okay, think of your camera head. It's divided up into a matrix. Okay, higher matrix sizes have ability to record finer amounts of detail, and then larger matrix sizes, when we do more of them, it requires greater computer space. Let me go to the next thing. This is kind of a graph I used to help you understand it a little more. So the kind of yellowish color here, that represents your camera head. And then what I've done is I've laid a matrix, a fake matrix, over the top of your camera head. So you can literally see that the matrix represents the different locations on your camera head. Now, these are not to scale, right? Because your matrix pixels are going to be much, much smaller. We use anything in NukeMed, anything from a 64 by 64 to a 256 by 256. This is like, I don't know, like 17 by 17 or something like that. So these are not to scale, but it's to give you an idea that there's small, you can divide it up into a smaller matrix or a large matrix. And basically it's like a square mosaic representing the surface of your crystal, okay? Each pixel, each square in this matrix has a unique memory address assigned to the computer. So the computer says, I'm gonna watch this spot and I know what to do with it to record it on my screen, right? For each detected event in a pixel area, the number increases by 1. So go back here real quick. Notice there's a bunch of zeros on here, and then this place right here, there's a 1. That means there's been an event detected there. Each time an event is detected or a photon hits that location, it's going to go up by 1. You guys have watched this happen on your cameras, I'm sure of it. When you're watching a hide area, you're watching anything, and you slowly watch all those hit and you watch your image form. What's happening is every spot on that matrix is saying, okay, I got another one, I'm gonna get brighter and brighter and brighter and brighter. So this might go 1 and then become a 2, 4, 5, 6, 7 because there's your patient's giving off photons right there, right? So each one of them increases by 1. So here's an idea of how many picture elements are going to be divided as you go up. So if you're using a 64 matrix, you're going to have 4,096 picture elements and so on and so forth. It's going to get bigger, right? So to give you an example, if you had a 40 centimeter field of view on your camera head, which is pretty average for a gamma camera, and you're using 128, then each pixel would be 3.1 millimeters. So to represent 3.1 millimeters of tissue or space on that camera head, okay? The way you would figure that out is I took 400 millimeters because we're going to want to end up with millimeters at the end. So I made 40 centimeters, 400 millimeters. So 400 millimeters divided by the 128 pixels gives me 3.13 millimeters per pixel. So that's how you figure that out. So for things like I will let when Brandon goes through your classes with you and he talks about the different types of exams you do, he'll probably mention like what matrix size you use for what exam you're doing. But as a general principle, I want you to think of the fact that a bigger matrix size, which gives you a bigger pixel amount, can record events faster because it sees a bunch of radiation in a bigger spot than can a smaller pixel. So things like, let's say, a bone flow, where it's going to flow by and be gone, you're going to be using like a 64 matrix because you're going to need to record that information quick. You're going to want to get enough counts quickly in 1 pixel. Whereas something that's more detailed, you might use like a 256 because it's just sitting there, you're acquiring a static, and you just want really good detail in every little pixel, you're going to use higher. So that's general. Look into that more, especially as you're studying the exams you do and why you would use a matrix that you use. But that's the principle behind why we use what matrices we use. And then there's really two digital types of formation. One is the frame or matrix mode, which I just talked about, which is just the XY coordinates, creating one's increased intensity in each pixel on your screen or on your camera, which then translates to your screen. The other one is list mode, and in list mode, what happens is your camera records what's happening in its pixel, and it records it like a digitized address. It records addresses sequentially in time, so it records. It's almost like having a list of addresses that the camera stores, and then later when you go to develop whatever picture you're looking at, you'll go back and the camera will grab certain parts. So a good example of this would be like, how when you do like a bone flow, if you just left your camera on in matrix mode during a bone flow, it would flow in and then pixels would start gathering and you wouldn't have anything where you have like your bone flow at the end, you can show each picture and you're walking through that flow as it comes in. The reason you can do that is because it's been in list mode. It's gone and said, okay, grab everything out of the first few minutes of the flow, everything out of the first few seconds of the flow, the next few seconds, the next few seconds. Another thing that's done in list mode is in cardiac, you can actually calculate an ejection fraction, which is how the heart is beating, right? And the reason you can do that is in list mode, because you can say, here's all my addresses of all this data happened when it happened. I want you to grab everything for systolic and make it into a picture, and I want you to grab everything for diastolic and make it into a picture. And now I can look at those two. I can look at a systolic image and a diastolic image, right? Because I've done it in list mode. Most cardiac stuff is done in list mode. Most PET stuff is done in list mode, at least with cardiac. So those are kind of your two different types of modes. So now we're going to get into SPECT. So a lot of the principles of the camera are not going to be repeated here. We're mostly going to look at how a SPECT camera functions in terms of doing a scan. And then we're going to talk about reconstruction, because where on a gamma camera, you're looking at like your matrix mode and you just simply form a picture you can look at. Here, we're going to be forming a 3D image. So we have to talk about reconstruction and how that works. So SPECT stands for single photon emission computed tomography, and it uses tomography to represent a 3D version of activity basically in time and space. Okay, so originally these were like single head, and they would rotate around the patient and stop and shoot and gather data. Most cameras now use two heads, one on each side, 180 degrees apart. And so for most specs, you don't have to go 360 degrees. You can actually go 180 and get a projection of every side of the body by doing 180 degrees. And that's on a dual head, which makes things quicker and faster. And most cameras have that now. You may work in departments that still have a single head, and that's fine. You can do it with a single head, just all the way around. There's a couple of modes. You can have step and shoot, which is where the camera will sit in one spot for a while. It'll shoot, gather data, then it will go out and move, and then stay in another spot for a while. That's step and shoot. There are some cameras that will continuously image, so they'll very, very slowly move around the patient while they're constantly gathering the data and then separating that out via list mode. And so those are kind of two ways you can do it. Most of the time they operate in H mode. Cameras can operate in L mode, where the two heads are like this. You see that in cardiac studies. The reason a cardiac study does that is because your heart sits on the left-hand side. The left ventricle, which is what you mainly image in cardiology, is sitting out towards the lateral side, the left-hand side. And so if we put our camera in L mode and we start here, we're getting clear over on the side of the heart, or the septal side. And by the time this has gone just 90 degrees, we're all the way back around to the back of the septal side. And so we're using a 90 on a heart, because it's mostly left side. We can really get almost 360 degrees by using that L mode and only going 90. So L mode is used for some of those kind of things on a SPECT as well. One thing that's really cool on most SPECT cameras nowadays is they will have body contour orbits. So a camera can just make a circular orbit, which is the image you see right here. You have a perfect circular orbit that the camera is making around body. However, with body contours, which is where there are devices on the camera that can see where your patient is and adjust as they go around, you can get better resolution. Like we mentioned before, remember distance, getting a larger distance always reduces resolution, and bringing your distance closer will always increase resolution. So you'll notice that there's a circular pattern here, and that on the lateral sides of the patient, you're getting better resolution than you are on the anterior and posterior of the patient. Whereas when you're doing body contours, you get an ellipse and you get closer on all sides of the patient. So again, greater resolution when you use body contours. So if you have them, use them, because they really help. I understand there are situations where you can't, because your patient habit is a bunch of random things, but where you can use them, because you'll get better images on your reconstructions. There are two types of reconstruction. That's really, and I'll go back real quick, because that's really basically like all I'm going to say about the functionality of SPECT. That's how it works. It's pretty simple. A lot of cameras have SPECT CT, and we'll mention that when we talk about PET and CT. But that's the basic functionality of how a PET scanner works, is going around in 360 degrees and acquiring images. Those images have to be there we go, reconstructed, right? So that they can be a viewable image, because they're 3D We've taken a bunch of projections and now we need to find a way to put those projections together in a way that we can see the image. So there's two things we're going to cover. One is filtered back projection. That's the original method used in SPECT cameras. It's still used today. It's very widely used. And then there's iterative reconstruction, which is more based on some mathematic ways of reconstructing. We'll kind of cover these both. Both of these can be somewhat, they can feel somewhat convoluted and hard to understand. I'm going to do my best to help you understand them. There's also a video on here that I show you that's really good. And then I would just encourage you to go through both of these things and read them until you understand them. But in filtered back projection, each image acquired at each camera angle is called a projection, right? So as that goes around, you're getting projections. You have, I mentioned, let's say we're using a 128 matrix, right? So you have 128 locations or pixels along that. That would represent like the amount of slices that you can get. So when you look at an image like this, just think of it as like one slice across the camera head. And that'll be helpful for you as we try to understand this. So each projection is divided into axial slices according to the matrix size. Back projection assigns values to the projection along all points of the acquisition. So what that means is that down here in our example, we have this dark spot which represents some sort of radiation source, say it's a gallbladder. Way off of where it should be, but let's say it's a gallbladder. So it's giving off radiation and it's hitting the camera. Your camera is likely seeing values along the whole camera head, right? You guys have seen that as you've looked at a high day, you've got some diffuse technetium throughout the body, but you've got it concentrated where the gallbladder is, and even outside the body. Sometimes if you really brighten up a camera, you can see things, right? They're seeing some radiation throughout. So they've tried to represent that as a little graph on this image. So right here, you're seeing like greater intensity and then less intensity as it goes out on the body, right? So what filtered back projection is, it takes that slice and it throws the intensities of that slice for one camera position or projection, and it throws that across the matrix. So all the intensity goes across the matrix. That's what you're seeing right here, okay? You're seeing that whole entire projection thrown across the matrix. That's back projection. It's back across the matrix. And what happens is you get that for each camera head position where it stops. Every time it stops, you get a back projection thrown across the matrix. Eventually, as you throw enough of those back projections across, wherever more intense intensities cross, the camera is going to record those as the hottest intensity portions, and that's how it begins to create the image. Again, I'm going to show you a video in a minute that will make that even more clear. Each projection is kept in what are called sinograms. So if this was like a body part, this looks like some sort of phantom, right? But if I took this phantom and I grabbed it and I sliced it into three pieces, the top, the middle, and the bottom, and then I laid them out, they would look like that, right? Like a slice would be different. So if I took a projection, so the camera's in one position, and this is what I get. This is my picture projection I get, and then the next time the camera moves, I get this, and the next time the camera moves, I get this, and the next time the camera moves, like this. So each time it's getting that. Then what would happen if I then took, and your camera is going to make more than 3 slices, but for the ease of explaining, here's the 3 slices. So if I took this top slice right here and I threw it down here, and then I took the next top slice of the next projection and I threw it down here, and I took the next top slice and threw it here, and the next top slice and threw it here, what I get is called a sinogram. So what this represents is it represents that top slice of every projection that I grabbed, and it throws it into that sinogram. So it's like the place where it stores the data for that one particular slice at every single projection. And so there's a sinogram form for every single slice. So if you're doing 128, you're going to have a lot more sinograms, right? For each individual slice. That sinogram is the data that when the camera goes and throws everything back across the matrix, it's going to take that sinogram. That's where it grabs its data from for each time it throws everything across the matrix. Okay, let's watch the video. It explains it. Seeing it is much better than I can explain it. And then once we watch it, I'll explain it one more time. Okay, so, and then we'll read exactly what's up here because it'll describe it good. Okay, so as soon as this comes up, I'm going to pause so you kind of know what you're looking at. So part 1 is the acquisition. This represents us acquiring the data. Okay, I'm going to pause. So what's going to happen is you're going to see a sinogram formed here, which again is each projection, that slice of each projection, so the sinogram data is going to be formed here. This will kind of just show the camera projection, or it represents as the camera goes around. And then this is going to be our object that we're scanning, right? So let me let this portion of it play. So there's our object. We're projecting from anterior to posterior here, and that's our camera head. And it's going to go, and we're getting all the projections. And notice that the sinogram is forming as we go around, all the way around, and we've done every single projection. We've formed a sinogram. So that's all the data that we just gathered. Okay. The next phase is going to be the reconstruction, which is what I've been attempting to explain to you here. Okay. So again, I'll pause momentarily. Here we're going to have the original object that we just imaged. We're going to watch the reconstruction as it forms. Our sinogram data that we're grabbing from is here. And then this is the projections. Here we go. And I'm going to pause right after it starts. Okay, I'm going to pause right here. So what you've seen, what you represent, this is the matrix, right? So they've taken the first projection, the first slice, the first projection, the first slice, and they've thrown it across the matrix. So the values all go across the matrix. It's not individual placement. It's just, here's how much value I see across that matrix in that area. Boom, I'm gonna throw the whole thing. So now watch, because it's going to start throwing values across for every stop of the camera. Here we go. Okay, now that you've watched that, I'm going to read these bullet points. I'm just going to straight up read them. So think of what you just watched, and I'm going to say back projection assigns values in the projection to all points along the line of acquisition, then projects them back across the image plane. This is repeated for all acquisition angles, and new values are added to previous ones. As the number of angles increases, the back projection improves. Okay, I want you to watch that video again. Again, essentially what's happening is wherever things overlap, higher intensity is recorded, and as it goes around, it then records. And basically, you know, like where you have this liver over here, that was recorded as a higher intensity because there's more radiation there, because more times crossed along that back projection of each slice. Okay. So let's see, let's go here. Okay, so that's filtered back projection. Again, go over and watch that, and you'll get it more as you go, as you watch that a few times. And I'm happy to answer any questions on that too. The next one, if you thought that was a little confusing and hard to understand, iterative is a little worse. I'm going to tell you, I want you to understand filtered back projection and how it works pretty good. The iterative, I'm going to give you a simple understanding right now. I just want you to understand that it's a mathematical way of figuring out how to reconstruct an image. Now I'll explain it to you, and know that if you at least understand it's a mathematical way of reconstructing an image, you'll probably be okay. I would try to understand it more than that, but that's going to be enough to get you by. So, iterative reconstruction. What's happening is the camera gathers the same data, so it has all the projections. One of the reasons, oh, and I probably should have mentioned this, filtered back projection is called filtered back projection because when this went, you notice that there was a bunch of extra kind of junk out away from the body because of all that stuff going through. They apply a filter to it, and we'll talk about some of those filters in just a minute. But they apply a filter to get rid of kind of that excess area and only allow what's overlapped to stay. Okay. So the only reason I mentioned that is because one of the reasons we use iterative is if it's a system where the camera looks at the projection that you've made, it looks at the projection data, and then it makes a guess, and it says, this is where I think I should place intensity. And then it goes back to each projection and see if it matches. So it doesn't actually ever throw the projections across the matrix. And what this does is it helps it so that we don't end up with all that junk we have to filter out in the end. So here's how it works. These four boxes would essentially just represent like a body, right? And so as radiation is gathered on your camera head, it's going to be of a certain intensity, okay? And all the camera head knows is that across, going vertically across your body this way, it recorded a certain intensity on each projection, okay? So if we started out with this that represents the body here, our first intensity is coming out so that the camera head would be, sitting, well, let's see, which way did they go? Yeah, so the camera would be sitting down here. So we ended up in the body, there's an intensity of radiation, we'll say it's a 5 here and a 6 here and a 7 here and a 2 here, but the camera doesn't know that yet. All it's seen is that when it measures everything coming across in this direction, it at least knows that it's got an intensity of 11, but it doesn't know that the 6 is here and the 5 is here. It could be 10 and 1, it doesn't know. It just knows that when it measured that intensity that came through, it was an 11, and they measured the intensity that came over here as a 9, okay? So what it's gonna do is it's basically gonna guess. And it's going to say, well, I have an 11 here and I have 2 pixels to fill. So I'll just put 5.5 in each of them because I know that those two together have to add to 11. So it puts 5.5. And on the other side, it says it's 9. So I'm going to put 4.5 on each of them. Cool. Okay, great. Then it goes to the second projection that says, this is my prediction of what I think it's supposed to be. Let me look at the next projection that the camera took and see if I'm right. Well, it looked at the projection and it came back that actually the projection that's now the camera head's over here. So we're measuring coming through this way, the intensity that comes over here to the camera head. That actually this was supposed to be a 10 coming through this way. It measured a 10. And this way it also measured a 10. So it went back to what it did and it said, well, I did a 5.5 and a 4.5. And that's not gonna equal 10, right? So something's different. It actually is gonna equal 12. So I need it to equal 12. So what it does is it said, on my next guess, I'm gonna go ahead and add 2 and make it a 12. And down here I measured through and I'm going to go ahead and minus 2 and make it an 8. And the reason it did that, I said that a little wrong. It saw it as a 10, both of these are 10s, but it's using this projection, the real projection now. So the projection going through this way is 12 and 8. And so when it looked at that, it came up with 10, but when it looked at it, it was like, oh, I'm supposed to be 12 and 8. Well, darn, I better go back. So it goes back and it says, to make this 12, I'll get 2, and to make this 8, I'll have minus 2. Sorry, I said that a little bit weird at first. So now it says, okay, well, if I know I have 12 and 8, then I'm going to do the same thing and I'm going to divide these up. I'm going to make this one 6.5, and I'm going to make this one 5.5. I'm going to make this one 4.5 and 3.5. And now it's going to look at the next projection, which came through at an angle going this way. Actual projection says it's 13. When it measured these two going through at an angle 4.5 and 5.5, it again got 10. So it said, well, I was wrong again. So now I'm going to go and I'm going to add 3 to it and get 13. And now I'm going to take that 13 and divide it between these and make it 6 and 7. And so these are what you call iterations. Each time the camera guesses and then goes and looks at the data, it's guessing again what it should be, till eventually it's made enough guesses that the data that it guesses matches the actual true data. So we get 5 and 7, 6 and 2. Now again, this seems weird because you might be like, well, why doesn't the camera just use the data, throw it across the matrix and call it good? And the reason again is because with iterative, you get a much better reconstruction because it doesn't have to throw everything across the matrix. It can just simply look at and guess and do all these mathematical equations to accurately predict what it should be and then place a pixel exactly where it's supposed to be instead of random stuff all over the place and hope for the best on what's crossing, okay? So that's the advantage of iterative reconstruction, but you can imagine it takes a lot of computer power, right? Because you're going through all these mathematical equations. I have a few iterations here and I have 4 pixels. Remember that even on our 64 by 64 matrix, it was like 6,000 something pixels. So you're gonna be doing this for 6,000 of these things going across. And you're going to have to do enough iterations to get to the right answer. I mean, the math would be like, boom, like this is hard to understand with 4 pixels, right? And so it's again, I want you to understand it's a mathematical way where the computer looks at a projection and guesses mathematically, and then goes back and compares, and then does it again, which is the next iteration, and then does it again until it gets it right. Iterative, it's iteratively doing something, each iteration, right? So on here, I kind of put the advantages, disadvantages of the two versus each other. So iterative has the advantage that if you have, like, let's say you have an artifact in one of your images, like one of your tubes has gone out, something's happened. When you do filter back projection, you're gonna end up with like ring artifacts, because that artifact is gonna show up all the way around in every image, so you can have weird artifacts. Whereas if you use iterative, that would be with filter back projection. If you use iterative, you don't get some of those artifacts because the computer mathematically is going to see what's supposed to be there and fix it. Less noise, less streaking, overall just better image with iterative reconstruction. Filter back projection, it's simple. You don't need massive computer memory, and it's very quick because it pretty much can kind of do it instantly. Now, there's an argument to be made as we advance with computers that iterative is really fast nowadays, but it still takes time to reconstruct an image, and that's because it's going through those iterative processes. Disadvantage again is the computer and taking a little bit longer, and then filter back projection, again, you can get some of the noise, the streaking, the stuff on the outside of the body, ring artifacts, all those kinds of things. We're talking about filtering now. Filtering is kind of how we correct for that filtered part of the back projection. Really, when it comes to filters, there's two types of filters that help us sharpen up our image or change our image to the way that we need it. You have a high pass and a low pass filter. So what I want you to remember here is high pass filters removes low frequencies. Low frequencies tend to be responsible for more smooth or blurry imaging, and high frequencies tend to be responsible for sharp or model-y looking imaging. And so with a high pass filter, it means it lets the high through. It's kind of like Gandalf, you shall not pass. So high pass will let the high stuff through, it'll let the high pass through, and then low pass will let the lows pass, right? It'll let the low through. So high pass filters are going to sharpen an image, and low pass filters are going to smooth out an image and make it, you know, a little bit just smooth, reduce noise. So one of the main ones that's used, and this is the one that's generally used to do filter back projection, is called a ramp filter. It is a high pass filter. So you'll notice on this chart that the filter function, so here it's saying how much of the filter is applied, and then on the lower half it's saying like the frequency. Remember when I talk about the low frequencies and the high frequencies? So what you'll notice here is that a ramp filter is a high pass filter. Why? Because look at how much it's cutting out the low end, and it's allowing the high end to go through. Again, so it's kind of sharpening everything up, and it's going to erase blurring and get rid of some of that garbage that's on the outside of your spec reconstruction. Two of the really common filters used in nuclear medicine are a Hanning filter and a Butterworth filter. So a Hanning filter is a low pass filter. So again, letting the low frequencies in and cutting off the high frequencies. So in the case of like a lot of times when you do a spec scan of a heart, it can be pretty model-y without a filter applied, but as you apply more filter, it smooths the image out, makes it better to look at, and it's easier to see. I would argue that the best image probably is the second one. Like by the time you get down to this 0.4, it's really smoothed out, but you can play with the filter when you're processing your imaging, and that's what it does. And then there's a Butterworth filter, which is very similar, but what you'll notice here is that it keeps more of the low end than Hanning. The Hanning kind of keeps low end but cuts it off quick, whereas a Butterworth will kind of keep more of the low end and then cut off the high end at a certain point. And so you can see kind of the difference here. Similar thing, again, it's a smoothing filter. I would say the 0.4 looks pretty good on this one because it's keeping more of those low end ends and then cutting the highs, you know, actually it's keeping more of the high end in really because it goes out further. And so it's a little better image. But again, these aren't really great images of a heart anyway. They're not how it normally looks, but you get the idea. That's the filtering. So yeah, so main filter, ramp filter is that main high pass filter you see, and the Hanning and Butterworth are the main low passes. So just understand kind of which ones are low pass, which one's high pass, and then understand what that means. And again, if you just think about it, low pass filter lets the low end through. Low is responsible for smoothing. High is responsible for sharpening. Okay. All right, so now we're going to get to the QC, and that's basically the last thing that we need to look at, and then we'll be done. So for the camera QC, for the gamma camera, I don't know why I put scintillation. It's scintillation camera, but I should just stick gamma camera up there. There's kind of four main things that you're going to do, or that you need QCs that you need to know. There's a uniformity. That uniformity is done daily. There's also a couple of different types that you would do at other times, but remember that your uniformity is done daily. Spatial resolution is typically done weekly. Center of rotation is done weekly, although I have seen some books that say monthly. Know that it could be weekly or monthly. I know most facilities I've been at have done it weekly, and then there's peaking. Now, your license may require some additional tests, or it may require you to do it more frequently than what I have listed here. What I have listed here is probably what the general thing that you would see on the boards. Read through your book. Again, those are you'll definitely have stuff like this on your boards, like how often do I need to do a uniformity flood? Okay. Now, all of these floods, or excuse me, all of these QC quality control procedures can be done intrinsic or extrinsic. Okay. And basically that means with the collimators on or the collimators off. Okay, so that's what we mean when we say intrinsic. Right, intrinsic is with them off, extrinsic is with them on. Intrinsic stuff is gonna look more at the crystal, really good for crystal, photomultiplier tubes, some of that. With the heads on, it's just more system in general, what your image would look like. Also, they use a different quality control source of radiation for these. You can get, there's like sheet sources, there's phantoms that you fill with water, there's little point sources, there's a bunch of different types. And sometimes those can vary and be different depending on your camera and the manufacturer that you have for your camera. So let's talk about uniformity. So two methods, intrinsic. So intrinsic, we're going to remove those collimators. For this one, you're going to take a source of technetium, and usually it's a point source, so a small source. And that source is usually held kind of a ways above the camera so that it can shine down onto the entire face of the crystal. Typically, 30 million counts are what helps determine uniformity. So when you do a uniformity, your camera is looking at every photomultiplier tube, and it's looking to see that they're within a certain range of seeing similar data and agreeing with one another. Your camera will do a uniformity correction with 30 million counts, which is where the software will look and it will say it's within a close enough distance of each other. They're all seeing similar counts, but I'm also going to do a correction, which means I'm going to adjust where things are a little lower than they should be and try to equal everything out to kind of a zero sum. Okay, that's why they do the 30 million counts, because they're really long and they can do that uniformity. However, a 5 to 10 million flood can be required just to see if the uniformity is out more than 5%. So that's the thing you're going to want to remember. 5% is your usual number. So when you go do floods in the morning and you count to 5 million and you come up with those little numbers at the end, 3.4 or whatever, FOV, field of view, blah, 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 you basically don't want those to be more than 5%. If they're more than 5%, then something's going on with your camera. That's out of tolerance. Okay. And then of course, when you look at a flood in the morning, you also want to just visually look at it to see if there's any spots that are looking weird, or there's a dark area, or it's an area that's too bright, anything that's out of visually out of whack. Okay, so the extrinsic version is we keep the collimators on. We're going to do the same type of thing. We usually use a solid sheet source. You usually buy those sheet sources from a company. And what they've done is they've taken usually a cesium source and they've spread it evenly across the entire sheet. It's a solid material in there. And so there's no liquid or anything, but that's what your sheet source is. It's a solid cesium source. And so they use cesium because it has a pretty good half-life. And that can be placed on the camera or a few centimeters above. I've seen some techs that will put some cups up and put it on. You really can use it either way. But usually you do like a 10 million, sometimes you do a 5 million, depending on your facility, your camera. But again, that same 5% uniformity to check for general uniformity on a daily basis needs to be there. And this is kind of what a good flood should look like. You see nothing, there's no one spot that's kind of weird and out of whack. It's kind of a uniform look across the whole thing. The next one is spatial resolution. So again, you can have intrinsic and extrinsic. For the intrinsic, we're going to remove the collimator. This uses a quadrant bar phantom. You want to be careful because the bar phantom has lead septa in it and it's super heavy. So if you have your collimator off and you drop that on your crystal, then you've cracked your crystal, your camera goes down, and it's really expensive to repair, and you're not going to be able to scan patients. So you need to be very careful. But we usually do with the intrinsic, we do a point source, 10,000 to 40,000 counts per second. 3 to 5 million counts are usually required, and then you look at that to see that you can see the smallest bar pattern on there. If you can, then you're in good tolerance. And really, these are just visually inspecting these. Extrinsic is very similar, except when you're going to use the sheet source instead of a point source. Done with the collimators on. Usually, you're going to do it with the low energy collimators with bar phantoms. That's usually what your camera's calculated for. And so here's an image of that. You should be able to see these spaces between these smallest bars down here on the phantom. The other thing I would tell you that's really good practice to do is that each time you do that, if you lay it on at one angle at one time, then do it 90 degrees the next time you do it, just so that you're not missing slight things that can have slight variations in between the spaces of the septa. So if you move it around at different angles, then you kind of cover spatial resolution on your entire camera. And then the last one I'll show you, this is spatial resolution for when you do SPECT, right? Because when we reconstruct an image, we have to know that our image can reconstruct in a good resolution as well. And so this is called the JSAC phantom, and basically you put some technetium inside, it's water filled, and then there's all these little circles and kind of columns. And then what you're going to do is set that, you're going to put that on your camera, and you're going to do a SPECT scan of it. And then you end up with slices that look like this. And it's kind of the same thing. You want to be able to see and resolve those smallest circle patterns and be able to see the resolution on them. So again, another visual way that you look at it. But it's going to give you slices just like any SPECT would give you. And just look at all those slices to see if you can resolve those circles. And then the last one is centered rotation. For this one, you get a point source. That point source is usually held out in the middle of your camera on like a small rack or a small bar. And then you acquire around that. And essentially what it's doing is it's seeing if that point source that's in the center of your camera is accurately represented at each SPECT step along the way in time and space, right? And the camera will be able to detect if it goes out of tolerance at all. Usually you want to see a shift of less than 2 or 3 millimeters to get an accurate reconstruction when you do a SPECT. So that's the COR. It just goes all the way around. This one is another one where I've seen books. Every facility I've been at, they do it weekly. I have read one book that said it was monthly. Again, I would probably advise weekly on that one and give you that one to answer your boards. So, and that's it. We are done. That was pretty long. Got through it in a couple hours. So again, let me just end the sharing here. That. So it looks like everyone's gone, which I'm glad. I want you guys to make Sean's class. So when you come back to listen to this, the only thing I would say is, again, there's a lot of stuff there. Go back and watch the lecture, look at this, read the chapter 11 in your book, and this stuff will all come to you. The nice thing about this particular lecture is you use the Gamma camera every day. So I want you guys, as you're using your camera, to kind of think through some of this while you're using it and apply what you're thinking as you're doing it, even though you don't see these processes happening when you're doing a scan for the most part. There was on test number 2, and it will be, I originally had it available today. I was going over it, and something happened to my question bank, and some of the questions were gone. So I'm going to hurry and review that over the next couple of days, and I'll just make sure it's available by Monday. I doubt any of you are running to take it in the next 2 days anyway, but it'll be available probably by Monday. So that's the only assignment you have in terms of next time we meet. I mean, we're meeting on the 30th, which again is a Wednesday. Remember that, so that we don't have to meet on Halloween. But yeah, watch this, do your tests, finish up your math, do your test corrections for the last test, and then again, let me know if you have any questions or you need anything, and I'll try to be quick with my answers. So again, thanks for letting me alter the schedule a little bit today, and we will see you next time.